The next section we're going to talk about is Ohm's Law and power. Now this is important because it's one of those basic things that everyone's going to expect that you know, like what's the square root of 25, what's Ohm's Law, how do you take a common denominator, how do you do the quadratic equation. This is stuff that everyone's going to expect that you know is Ohm's Law. So the idea behind Ohm's Law is if we're going to say that the amount of charge flowing into and out of any section has to be equal, as the resistance increases, then we have to increase the pressure. So if you remember that picture that we had that kind of looked like this, we said there was going to be high pressure here if the current was coming through this way, and low pressure down. Now, anything that's flowing in to an area, so if we kind of zoom in on that area, has to flow out. So if the current has to stay constant, then that means that the pressure has to increase as the resistance increases. So as this gets narrower and narrower, the same amount of current that goes in still has to come out. So that pressure difference has to get even greater, because there's not like a little like lounge where the currents can like hang out. I don't know what this is, a current hanging out. Look, they're hanging out. I don't know what they're doing. But anyway, there's no place for the current to hang out, so it has to keep going, which means we have to increase the pressure. So the way that we do this is we describe V being equal to IR. Okay? So basically that if you want the current to remain the same as you increase the voltage, you also have to increase the resistance. So this is the kind of the way of describing it that makes sense with the way we're saying it, is for the I to stay the same if you increase. So if like the voltage is 5, then the resistance could be 5 if say the current was 1. Or if it's 500, the bottom has to be 500. Or if it's 5 gazillion, the bottom has to be 5 gazillion. Okay? But generally, V equals IR is the way we see it written. V equals IR. So that's Ohm's Law. Now, in addition to Ohm's Law, we also have a relationship between current and power. So just to make sure we're cool, voltage is measured in volts, and the abbreviation is V. Resistance, as you remember, is measured in ohms. We call it R. So yeah, it's measured in ohms. Current is measured in amperes, but usually you'll hear people just call it amps, and we'll abbreviate it with an A. Thank you. Now power is, whenever you get your electricity bill, it's measured in megawatts. So we measure power in watts. Okay, so we have that P is equal to IV. Now this whole capital I versus lowercase I thing, some people use capital I's only for DC current and lowercase i's only for AC current. Do note that for all electrical engineers, I is not the square root of -1 because I is current. So actually for electrical engineers, J is the square root of -1. Neat fact. Okay, so if you see me write it in capital letters or lowercase letters, just know that we use those pretty much interchangeably ish, because again, we don't usually use capital letters for direct current, but that's okay. So I'll just write everything in capitals, so I don't have to worry about it. All right, so one of the things that we can do, so we've already got, hold on, I'll start with this. What we already have is V is equal to IR, so that's Ohm's Law. That's kind of one of your standard things. But the other one that I just wrote a minute ago is P is equal to IV, or that power is equal to current times voltage. If you have a hard time remembering it, you can think of it as poison ivy. Okay, kind of works. Now, if you are perhaps like an electrician, or if you've had experience doing this in the field, one thing that you might be a little weirded out by is the fact that we use V for voltage, and other fields use E for potential energy. So if you feel like these equations look familiar, but shouldn't there be an E in there somewhere? Yeah, but in engineering, we are not calling it E anymore. We're going back to calling it V. So if you have P equals IV, why does it do that? If you have P equals IV, but V equals IR, then you could also say that P is equal to I squared R. Similarly, if you have P is equal to IV, but technically if I go in here, I can solve for I and get that I is V over R. So I could get that I is V over R times V. I could also get P is equal to V squared over R. So these are two other ways that we can represent power, but if you're like, I'm going to memorize the absolute minimum required to move forward, You can just memorize these two here that I've got boxed in my amazing 3D boxes, and then that will carry you through anything else that you're trying to do. So here's a good an actual example. A 100 ohm carbon composition resistor has a voltage of 12 volts across it. What's the current? What's the power? So this is kind of your standard, like, college algebra. I just showed you something, now regurgitate it back to me. This is just a plug and chug kind of problem. I always like saying that, plug and chug. You just plug in the numbers, you chug through the math, and then you get an answer. All right, so looking at this, we have that the resistance is equal to 100 ohms, and the voltage is equal to 12 volts. So if we're looking for current, I have V equals IR. So 12 equals I times 100. So current must be 0.12 amps. Or if it makes you feel better, you can say 120 milliamps. But let's leave it in amps. All right, then it wants the power. P equals IV. So P equals IV, because I've got my squares memorized. Power is equal to 1.44, and the units are watts. And so that's really what we're looking for, I guess, is just some basic literacy with these equations, just to get comfortable with it, is using P equals IV and V equals IR.